Okay, this is the lecture 4.3 on linearly independent sets and bases. Okay, let's first review. Obviously, we've already learned what linearly independent means, but let's quickly recap. So recall an indexed set of vectors, an indexed set of vectors, and then we can call it, let's just use v1 to vp, per usual, v1, vp, in some vector space v. And v is said to be linearly independent, if the vector equation C1 times V1, and then we have this linear combination, right? CP, VP equals the zero vector has only the trivial solution. Otherwise, the set is what we call then linearly dependent. And then we call some C1 V1 plus to CP VP, if we can get that to be equal to the zero vector, we can call this a linear independence, or sorry, linear dependence relation. Linear dependence relation. If we can achieve this getting to the zero vector with non-zero weights. So if C1 through CP are not all zero. In other words, if there's a non-trivial solution to the homogeneous equation, then those writing out what those weights are is what we call the dependence relation, meaning that the set would be then linearly dependent. Okay, so this is all recap. You should already know this, okay, from the first unit. If you don't know it, now is a great time to stop watching this video and go into the lecture on linearly independent sets from chapter, I think it was 1. So if you don't understand this, stop watching this lecture, go to the first chapter, and really make sure you review this, okay? Because this is kind of the key pin concept to understanding bases. And there's another theorem that we did before that's worth repeating here because it's important. An indexed set, so we have V1 through VP of at least two vectors, so of two or more vectors we want to make sure our first vector V1 is not the zero vector. This is linearly dependent if and only if some vector v sub j with j being greater than 1 is a linear combination of the preceding vectors. And we will look at an example of this here in a second. So we do 1 through j minus 1. Okay, so what this theorem is saying is that my index set of 2 or more vectors, so long as the first one is not the 0 vector, we can know that it's linearly dependent if one of the vectors in that set, essentially, that's not the first vector, can be expressed as a linear combination of the ones that came before. This is, again, a chapter 1 concept. We've already covered this, and I'm just recalling it because this is all important to bases and calling back important concepts. So make sure this makes sense, that it made sense back in chapter 1, because we need this understanding. Because now we can apply this more broadly. Here's an example. Let P1 of t be equal to 1. Let P sub 2 of t, that is very good too. P sub 2 of t be equal to t, and let P sub 3 of t be equal to 4 minus t. Okay, so I've defined 3 vectors in the polynomial vector space. P1 is 1, P2 is t, and P3 is 4 minus t. And you realize, okay, well, P3 here is actually just some linear combination of the previous 2 vectors, P1 and P2. So I could say then this vector set, P1, P2, P3, is linearly dependent. Why do I know that? Specifically in the polynomial vector space, because, remember, so those 3 dots are the word because I could write P3 of t as a linear combination of the other 2 preceding vectors. It's 4 times P1 of t minus P2 of t. Right? 4 times 1 is 4 minus t. And this is a linear combination. And so if this third vector is a linear combination of the previous 2, then we'll find that it's basically not contributing anything new. It's not contributing anything to the span of the original vector set. And what we're going to be doing is we're going to effectively be finding the vectors that don't contribute anything important or new to the span information, and we just cut them out. And once we get the most efficient possible set of vectors, in other words, we minimize the amount of information we need to span a set, that's what bases do. Okay? I mean, think about the English word basis for a second. A basis, that's a kind of a fundamental thing. That's a foundational thing. The basis on which you do something, the basis, the grounds, the foundation, the kind of the bare minimum things that you use to build everything. The basis of a house, the foundation of a house, your pillars. A basis is going to answer the question, how can I most efficiently span a certain subspace using the fewest possible vectors? Bases don't want excess vector information. We don't want sets of vectors that are bigger than they need to be. Preferably, we would have the fewest amount of vectors to handle, and so the basis is going to do that for us. A basis, by definition, is not going to have any excess vectors. It is the bare minimum number of vectors needed that are linearly independent of each other so that it can still span a desired subspace. That's the premise here. get rid of the excess waste, and have the most efficient set of vectors to get a very, very efficient description of the span of a subspace. So let's move on to the definition now of a basis itself. This eraser's not very good. Okay. Definition. This is the new stuff. Let H be a subspace of a vector space V and indexed set of vectors, and then let's call this index set script B is equal to B1 through BP in V. This is a basis for H. And we have two defining properties for the basis. If, one, our basis B is a linearly independent set, the second property that we need is if the subspace spanned by B coincides with the subspace. So coincides with H. Now that's a lot of words. I honestly don't like expressing this definition in words because all of this can be described with very, very simple math. Simply, I want to be able to make my H the span of script B, my basis. So if I have a basis and I take the span of it, and if that ends up coinciding with the very subspace I'm trying to span, provided that that set is itself linearly independent, I have by definition something we call a basis for that H. So there's really only two ingredients here. Make sure that you have a set of vectors that they're linearly independent, and after you have a linearly independent set of vectors, if their span spans your desired subspace, then bingo, you have a basis. Okay, so that's pretty much the only thing that's important here is remembering this linearly independent set. If you, by definition, it doesn't make sense to have a basis where the vector set itself is not linearly independent. If you have a linearly dependent set of vectors, then you need to remove the excess vectors so that it's strictly linearly independent in order for us to start thinking about the basis. So here's an example. Actually this is good review from the invertible matrix theorem that we've been covering. Let A be an invertible n by n matrix. And actually we can just call it, we can describe it with our A being equal to A1 to AN, those are column vectors. Then these column vectors, the set of column vectors a1 through an, I'll redraw that n there, it's not very clear. a1 to an, we know that this is a basis for Rn. How do we know that this is a basis for Rn? Well, because these column vectors are going to definitionally satisfy what it means to be a basis for its particular subspace, in this case, Rn. So let's take a look at those two. We know we need a linearly independent set, okay? So the columns of A, and recall that A is invertible here. So the columns of an invertible matrix, if you remember from the invertible matrix theorem, they have to be linearly independent, okay? So if that's given to us, is that these columns are linearly independent. Why? Because that's what the invertible matrix theorem guarantees us, is that since A is itself invertible, then the columns of A are linearly independent. And then the span of these columns, we span Rn. And again, this is from the invertible matrix theorem. So both of those are from invertible matrix theorem. And we see, okay, so this subset A sub 1 to A sub n is both linearly independent, and its span generates our desired subspace Rn. Ergo, that set of vectors, those column vectors, they are definitionally a basis, one of infinitely many bases for Rn. So that's a key thing to know. Just because a basis is like a foundational building block, think of the basis as like an atom, or maybe not an atom, but like a molecule, like these really fundamental components. There are a lot of different types of, actually, yeah, no, the atom analogy does kind of work here, because you have a lot of different types of these subatomic particles that can create bases for the same exact stuff, right? So there is not just one basis for Rn. And actually, for any given vector, in generally speaking, a given vector space is going to have many, many different bases. Now, not all bases are equally created. Some are more helpful than others. And so we have two really helpful standard bases that we commonly will refer to and use in application and also in some other problem-solving stuff. So I think I can actually fit those definitions here. So I'll put that here. So here's an example of a standardized basis that is really helpful. Let E1 through En be the columns of the n by n identity matrix. Identity matrix. I sub n is equal to, and then if we write it out with its column vectors, I sub n equal to, and then E1 through En, right? Then the set big script E is equal to my E1 through En. That is called the standard basis. The standard basis for specifically Rn. Standard basis for Rn. Because really think about it. I mean, what are these E1 through En vectors? If we want to visually think about it, they are kind of like the unit vectors. So like in the physics perspective, say I had x1 and x2 like this, right? Then E1, so this is R2. So E1 in R2 can be expressed as 1, 0, and E2 can be expressed as 0, 1. In other words, E1 is functioning as this first unit vector, which is often conflated with I in physics. And so this is E1, and this unit vector on the x2 axis is often, we call it E2 in linear algebra, but that's often conflated with J hat in physics, okay? And obviously, you can compose, you can use E1 and E2 to access, in any linear combination of these, you can access any point of R2. So these very trivially span R2, R space, and they are also trivially independent of each other because they're defining completely separate axes. And this is extendable, of course, to R3. If I had x1, x2, and x3, then now this is R3. So then what are my E1, E2, E3? Well, E1 now in R3 is 1, 0, 0. My E2 is now 0, 1, 0. And my E3 is 0, 0, 1. Okay, but again, these are familiar vectors. These are not new concepts. 1, 0, 0 is just the vector, the unit vector here in the x1 direction, and the E2 along the x2 direction, and now we just have a third spatial dimension we can visualize going vertically. This is an IJK, okay? So this standard basis for Rn is essentially saying the unit vectors. The unit vectors in any, but generalized to any size of space Rn. So we're not constrained to the confines of a two-dimensional plane R2 or three-dimensional space R3. We could have a concept and a description of the standard basis, this analogous concept of these unit vectors in higher and higher dimensions that we can no longer visualize. We call it the standard basis for Rn. There's another standard basis, and it's for polynomials P sub n. It's going to be basically each of the individual powers, like polynomial parts with the powers without any constant multiples. It's easier said, written than just spoken out loud, so I'll put that down. So the standard basis, for my polynomial space Pn is this set. Start with 1, which is t to the 0th power, then t to the first, t to the second, so on and so forth, until obviously t to the n. Because I know that any linear combination of these vectors is kind of what we mean by when we put together a polynomial that is at most degree n. Okay, so this is just the standard basis for Pn. In other words, this is how we fundamentally, trivially build and construct every single polynomial we have in the vector space of polynomials. Okay, we use this. This is a stripped down basis, standard basis for your polynomials. Okay, so those examples give us a slight taste, intuitively maybe, of what this new concept is. Let's work through some more examples here, just kind of to get this concept down. I'll leave the definition up still because maybe it'll be easier to refer to throughout the lecture. Okay, so here's an example. And this example is going to motivate a theorem for us. So let's define, there's going to be three vectors. So v1 is going 0, 2, minus 1. v2 is equal to 2, 2, 0. v3 is going to be 6, 16, minus 5. And then lastly, let's call H the span of these three vectors. Okay, so note, now I'm going to just give you this for the sake of the example mechanics, that the vector v3 is really just taking 5 times v1 and then adding 3 times v2 to it. Okay, so you can check those numbers for yourself, but for now, just accept that this is a linear dependence relation, right? So v3 can be written as a linear combination of the other two vectors. So that means that this set is not it is not independent. We have a dependent set that we are taking the span of. So immediately we should think, well, that's a red flag. This isn't even satisfying the first condition we have here for my definition. This is failing. Ergo, we do not have a basis yet. Is it possible to get a basis, though, out of this? Well, let's take a look. Since v3 isn't contributing anything to the span because it's just already caught up in the span of those first two vectors, let's just cut it out, right? So here's kind of the logic. That dependence relation tells us that the original set of three vectors is linearly dependent. Linearly dependent. And since, okay, well, what does that really mean? Well, that implies that this third vector v3 doesn't contribute to the span. To the span of my three vectors. Okay? And if it's not contributing to the span, then that means my H, which is the span of v1, v2, and v3, but we just found out that v3 doesn't contribute anything. So really, the span is entirely unaffected if we just chop it out and leave it with v1 and v2, which is, those are the only two vectors that are actually pulling weight here. And now, those two vectors are linearly independent. So we see that the remaining vectors v1 and v2, they are linearly independent. Okay, now fantastic. I have a linearly independent set of vectors that in fact spans my H. Well, gee, I just made a checklist and verbally said precisely the definition, the defining qualities for basis here, right? v1, v2 is acting like my script B right now. That set of vectors, v1, v2, is my B. It is a linearly independent set. And it is, so notice here, span of that set is that H. Is the span of v1, v2 H? Yes. Okay, so I have a linearly independent set, and the span of that set gives me my subspace that I want. So ergo, this is actually now a basis. So we started with three vectors, v1, v2, v3. That wasn't a basis because it was dependent. But now, after cutting out the excess vector, I now have a basis. So we can essentially get bases for subspaces by taking a set of vectors and then chopping out all of the vectors that don't contribute anything to the span. All of the vectors that make it a dependent set. Okay, so that's kind of the concept here. And we can describe that concept using the spanning set theorem. Okay, so here's that theorem. The spanning set theorem. Which is going to say this: let S be denoting some set of vectors v1 through vp, and this be a set in some vector space V. Then we also want to let some h be the span of those vectors, so v1 through vp. Okay, so first, if some vector, maybe we call it some v sub k, some v sub k in my set vectors S, if this is a linear combination, kind of like how in the previous example we just did, we showed that this v sub k, the v sub 3, is a linear combination of the remaining vectors, in S. Then, here's some set notation. This backslash is the set minus. It's basically subtracting elements from a set. So take my set of vectors S and subtract out the unnecessary, unneeded vector v sub k. So v1, v2 is v1, v2, v3 minus v3. Okay, that's really what's going on. So that operation right there is saying take a set of vectors, or just a set in general, and subtract out this subset from it. So I'm getting rid of the element vk from my original set of vectors. And that still spans H. Just how we found here that this smaller set, even though we chopped out a vector, it still spans H. Well, that didn't change. Okay, and then the other thing is a small little detail. If H is not just the zero vector, right? So if our H is not just the zero vector, then that means some subset of S is a basis for H. And this is not an exclusive subset. This is an improper subset, meaning that technically a set is a subset of itself. Like S is a subset of S. So the subset of S that could be the basis could just be S, but sometimes S has excess vectors. It has more than we need, and so even then chopping those out, that's a subset, and it can still be a basis for H. So that's the spanning set theorem. So let's go, there's one more example that I want to do, and this last example, or it's a pair of examples, is going to explain and motivate the last theorem here that's important. So I will now erase the definition. So if you haven't yet already, handwrite out that definition, make sure you got it, make sure you learn it, memorize it. And I just thought I might as well show you, because some of you may be wondering how I make my script B. To make a script B, start at the top, you'll come down, make a slight loop, and then make the first rung of the B, and then come out on top and kind of pass it over the first starting point, so it gives it a little stylistic look. So again, I start here, I come down, I make a slight loop, I don't close it all the way, and it's a little hard to make big. But on your paper, getting a nice cute little, that's not very good. With practice, you can get a nice script B, okay? So there's that. Do you have to use the script B? No, you can use a different symbol, but it's just fun to know some of those things. Okay. All right, example. we know how to find the basis essentially for the null space. We kind of talked about that in the previous lecture. So now let's do the column space, because we didn't really talk much about the column space. Find a basis for the column space of the matrix B, where, and I'll actually define this here, so B is equal to B1. Let's have 5 columns, and those 5 columns will be this: 1, 0, 0, 0, 4, 0, 0, 0, 0, 1, 0, 0, 2, minus 1, 0, 0, 0, 0, 1, 0. So you can already see that's an echelon form. It's a reduced row echelon form. So because it's in reduced row echelon form, let's identify our pivot columns. Pivot columns. What are the pivot columns? Well, here's a pivot here. There's a pivot here, and there's a pivot here. So we have B1, B3, and B5 as having pivots. So they're the pivot columns. And all the rest are the non-pivot columns, the non-pivot columns. So that would be the rest, B2 and B4. Okay, so why am I talking about pivot columns specifically? What's so interesting about these pivots? Well, observe how each non-pivot column, each non-pivot column is a linear combination of the pivot columns. I feel like now's a good time, in case I forgot to mention it, the column space of a matrix is simply all possible linear combinations, so the span of your columns in the matrix. So quite literally, I just want a basis for the span of these columns. Okay, so each non-pivot column, they're a linear combination. Well, the moment I hear that it's possible to describe certain vectors as a linear combination of the others, my brain says, wait a second, that doesn't sound independent. That sounds pretty dependent to me. If I can take some of my column vectors and express them as some combination of other vectors in that set, that's not contributing anything. All right, so for example, B2, take a look at B2, this 4, 0, 0, 0. That's basically just if I took the column 1, 0, 0, 0, and ended up multiplying that column by 4. So 4 times B1. That's a linear combination. B2 is equal to 4B1. So B2 is not contributing any new information for the span. It's not helping. It's just contained already within the span of B1. And then the other one, B4, let's take a look at it. B4 is the 4th column here. So this 2 and the minus 1. So what it's really doing is it's scaling up this 1 by 2, and then it is subtracting this 1. So we have 2 times the first column, right? So I could do 2 times this 1, and then to get negative 1, I can just subtract B3. So B4 is 2B1 minus B3. Okay, so my non-pivot columns are not contributing to the span. They are contained within the span of the other pivot columns. The pivot columns are the ones that are actually pulling all the weight here. So what we can conclude then is then let's just discard the vectors that aren't helping, the vectors that are not contributing anything new to the span. Discard my non-pivot columns, B2 and B4. Because once I do that, then I'm left with this set, S, I'll call it S sub B for now. S sub B is equal to B1 B3, because I got rid of B2, so now I'm skipping over to B3. I'm getting rid of B4, so I skip to B5. These three vectors, and only those three vectors, are needed to actually span what all of the vectors do, right? So if I wanted to really write this out explicitly, it's 1, 0, 0, 0, 0, 1, 0, 0, and 0, 0, 1, 0. This is not really that important to the example, but you can be like, wow, that does look suspiciously close to my standard basis for Rn. E1, E2, E3, etc., right? And so this set SB is now a basis. It is definitionally satisfying what we need and require for a basis for the column space of B. In other words, how do I want to describe the span of this? All possible linear combinations? Well, the span of that, get rid of the ones that aren't helping contribute, which coincidentally be the non-pivot columns. Keep only the pivot columns, and then once you keep only the pivot columns, you've now generated the basis for your column space. So generating a column space seems to be about identifying my pivot columns, keeping my pivot columns, and then getting rid of everything else. So you might be thinking, all right, that's fantastic, but that was kind of convenient. You know, we made the problem really easy because we just started off with a matrix that's already given to us in row-reduced echelon form. Most matrices aren't going to be like that. Like, what happens if I just have to deal with a straight-up matrix? That's why we have a comparing example. So think of this example as the same example, but like continued now. So suppose I want to find a basis for, so find a basis for the column space of A, where A is going to also have 5 columns. It's going to be 1, 3, 2, 5, 4, 12, 8, 20, 0, 1, 1, 2, 2, 5, 3, 8, minus 1, 5, 2, 8. Okay, now that's, you might be thinking, all right, yeah, that sounds more like something Pearson's going to make me have to do, right? Not as fun, more tedious. That's kind of just how it is. Now, you can check the work on your own time, but I will tell you right now, this is designed example because I prepared the lecture ahead of time, that A is row equivalent to B. In other words, if I started with A and I went through the typical row reduction and I row reduced A to B in row reduced echelon form, then B is the row reduced echelon form of A. Okay? So that's the relationship. If I take this general matrix A, I row reduce it, I get B. So we can side by side compare these things. Well, now think about that. So I know if I row reduce it, that's going to expose the pivot columns. If I'm just looking at this matrix, I cannot inspect this and just tell you what those pivot columns are going to be. I would have to row reduce it. So assume I had started with A instead of starting with B. I first take my matrix, I row reduce it to row reduced echelon form to identify what my pivot columns are. So my pivot columns are the same, not the same values, but same positions, right? Because if this is just, if I take this and I row reduce it to here, and those locations, the first column, the third column, and the fifth column, are my pivot columns, and that should be true over here as well. A1, A3, and A5, corresponding to the B1, B3, and B5. Notice that A1 is fundamentally a different vector than B1, because B1 is just 1, 0, 0, 0, whereas A1 is 1, 3, 2, 5. That's okay, because the position is what's important. The pivot column position is more important than the actual values inside of that right now, okay? So we start with a general matrix, do the work to row reduce it, once you row reduce it, we do that so we can identify which columns should be my pivot columns so that I can return to my general matrix A and say, okay, so then therefore the positions must be 1, 3, and 5 because that's what ended up being exposed when I row reduced it. Okay, so that tells me my non-pivot columns are then also corresponding to that, so A2 and A4. And you'll notice that all of the relative behavior is the same. Each non-pivot column is still just a linear combination of the pivots. So over here, if it's true that B2 is equal to 4B1, that dependence relation should be preserved even though we row reduced it. That's still going to be true here. Instead of B2, it's A2. And instead of 4 times B1, it's 4 times A1. And you'll notice, A2 is in fact 4 times A1. Go down to this. Here's my A2 column, 4, 12, 8, 20. Well, that is exactly what you would get if you took the first A1 column, 1, 3, 2, 5, and multiplied that and scaled it up by 4. 1 scales up to 4, 3 scales up to 12, 2 scales up to 8, 5 times 4 is 20. Fascinating. In the same sense that that relationship is preserved in the row reduced form, that relationship is preserved in the original matrix. Take advantage of that. That's the whole point of this theorem. Well, we haven't written it down, but we're building up toward it. And then this, B4 is equal to 2B1 minus B3. Okay, again, not the exact same vector entries, but that dependence relation is preserved. So instead of B4, it's A4. And instead of 2 times B1, it's 2 times A1. And instead of minus B3, it's minus A3. But who cares, right? The dependence relation is still preserved. This fourth column here is in fact what happens if I were to double the first one and then subtract away the entry and corresponding entry in the third, right? So like this 2 right here. If I doubled this 1 and I got 2, and I proceed to subtract 0, 2 minus 0 is in fact 2. 2 times 3 is 6, and 6 minus 1 is in fact 5. Double the 2. 4 minus 1 is in fact 3. 5, double that. 10, take away 2 is in fact 8. So even though these are fundamentally different entries, the dependence relation is preserved even after row reduction. And that's the key here, okay? That's going to let us know what we want to do. So I could say for A, SA, I'm going to only keep A1, A3, and A5 around, because those are the only ones that are actually doing anything. 1, 3, 2, 5, 0, 1, 1, 2, and minus 1, 5, 2, and 8. These are the actual vectors that form the basis, okay? So SA is a basis for the matrix, or not the matrix A, sorry, column space of A. Okay, so look at the pair of vowels and really take a moment to just digest that, okay? The row reduced echelon form gave us this insight. And then we stepped back and said, okay, let's ask the harder version of the question. Do those behaviors still work out? The answer is yes, okay? So here's the procedure, right? So if you really understand this, you could derive from this the procedure. General matrix A, get it into row reduced echelon form. Why would I do that? Well, I would do that because that makes it 10 times easier to identify what my pivot columns are. Once I identify what my pivot columns are, I take their respective positions and I take the corresponding respective positions in my original matrix A, and then then those are the vectors from which I take out of here that I say, those vectors form my basis for the column space, okay? That's the main result here. So we can summarize all of this with the statement of this very simple theorem. pivot columns of a matrix A form a basis for the column space of the matrix. A matrices, the pivot columns of the matrix themselves just automatically give you a basis for your column space for that matrix. So if you have, this is kind of the algorithm now, right? If I want the column space, a basis for the column space of the matrix, all I gotta do is identify its pivot columns and then make a set of only those pivot columns. And then there you go, you got a basis for your column space. So that is 4.3. So make sure you watch this recording before the lecture on 4.4, because the lecture on 4.4 is assuming that you're comfortable, again, with all this. Stuff starts to really build up on itself, and math already does build on itself a lot, but specifically in chapter 4, it's just going to be brutal to get far behind. So don't get far behind. Keep up with the lecture material, and keep asking questions, sending in questions as you have them. All right, we'll see you all.